So now that we've talked about the Executor Service, let's talk about how we can apply this to the PrimeChecker app that we've been using as a case study. And you'll see how we can use this Executor Service to overcome some limitations with the Executor implementation we talked about last time. So as with the previous Executor-based solution, this app is embarrassingly parallel. It's computing all the prime numbers, and it's or checking to see whether numbers are prime, and it's compute bound. So it'll run as fast as your cores will take you. This particular approach also shows how to handle runtime configuration changes more gracefully in Android. So if you recall, the Executor's version we talked about before didn't handle runtime configuration changes gracefully, but this one does. It also handles thread interruptions. So if you want to cancel the processing before it's done, you just click the little button here, and that'll go ahead and terminate it without having to wait a long time. It terminates it right away. As with the Executor implementation, this Executor Service implementation also uses a fixed size thread pool using the new fixed thread pool method. And you can see here that we also give it the get runtime available processors count, so it's going to have as many threads in the pool as there are cores on the machine. We're also going to have a user interface thread that's separate from the thread pool, and that's the thread that interacts with the user and takes the count of the number of threads, the number of random numbers to generate, and does all the user interaction. And it generates the random numbers and then passes them off to the thread pool for computation. And that way we don't block the user interface thread doing computations that run for a while. We also, because we're using new fixed thread pool, under the hood in the Executors utility class, that uses the unbounded linked blocking queue. And the purpose of this is to avoid deadlock. We don't actually have a deadlock here situation, but in other scenarios, which we'll talk about later, we might. So we have to be careful. This particular approach starts a second thread to wait for the completion of all the futures in the list of threads. And this is similar to your program for your assignment, where there needs to be a way to wait for the futures. Now, you don't actually have to spawn a separate thread in that case. You can if you want to, but I recommend you don't have to. It's doable, but you don't have to do it. But in this case, we have to do it. So we spawn a separate thread, and this thread is going to wait for the completion of all the futures in the list of futures. And the purpose of spawning a background thread to do this is to make sure that there's no blocking in the UI thread. The reason you don't have to do this for your assignment is that we already have everything running in a background thread to begin with. So the user interface thread is decoupled from the code that you're writing altogether because of the use of the model view intent pattern, which is how the architecture of the app is structured. But you don't have to worry too much about that. In this example, we didn't use that type of architecture, so we have to spawn another thread to run in the background. The way this is going to work under the hood is we're going to have something called a PrimeCallable. And this is going to be an improvement over our PrimeRunnable, which is how we had handled things for the Executor Service, in that we now have a two-way means of being able to determine whether a number is prime or not. Whereas before, if you looked at the PrimeRunnable that we talked about earlier, it only did one-way computations. And because it did one-way computations, as we'll see when we do the evaluation part, we had to embed some information into the PrimeRunnable object that knew how to get back to the underlying activity that was used to display the results. This approach doesn't require that, as you'll see in a minute. So PrimeCallable implements callable, which is a class that comes out of the box for Java and Java 5, so you can do two-way calls. And you parameterize the callable interface with the type of the result returned from the call hook method. And we'll look at that in a second. The constructor for PrimeCallable takes the prime candidate, which is the number, and stashes it away in a field. So it's stashed in there. And you can go back and kind of see how it worked. It's very much what we did before for Java Executor. And down here, we're going to have the isPrime method called inside the call hook method. So the call hook method is the method that's going to be called back in a thread in the thread pool when it's time to execute this object, this PrimeCallable object, this PrimeCallable task. And the call method is the method that gets called back by the Executor Service, And you can see what it does here is it makes a new prime result, and it passes in the prime candidate. That's the number we're checking to see if it's prime or not. And then we call the isPrime method, passing in the prime candidate, and that will go and chug away to see whether or not it's a prime number. Now, I showed you what the isPrime method looked like earlier. This is a variant of this that can be interrupted. We'll look at that shortly. And the result that comes back from call is the prime result. So it's going to be one of these guys, and that's just a little tuple. It's a little kind of a struct, if you will, that keeps track of the original number and the result of checking if that number is prime. So it's either 0 if it's a prime number, or it's greater than 0 if it's not a prime number. It's the prime factor, the lowest prime factor. And one of the nice things about using the callable versus the runnable is this two-way call mechanism allows us to eliminate any dependencies on main activity. So the callable doesn't know anything about the user interface that we're using here. So it means it's going to work a lot better when we go to the trouble of having to rotate the phone and destroy the existing activity and recreate a new one, which is kind of an Androidism, but it's a good technique to know in general. Okay, so here is the isPrime method, and this returns 0 if n is prime, or the smallest factor if it's not. And you'll see that this looks pretty much like what we had before. The main difference is every time through the loop, we check to see if we've been interrupted. And if we have been interrupted, then we break out of the loop, and we'll just return 0, which isn't really a good number, but it's the best we can do. At that point, we're done, so we don't care what the result is. So this is an interrupt. Now, interrupts occur when the user pushes the interrupt floating action button in the Android GUI, and as we'll see later, that generates a call that interrupts the thread here, the one it'll actually interrupt all the threads that are doing prime number computations. We'll talk more about thread interrupts later in the course. I mentioned them earlier when we talked about threads. There was a section on key methods in threads, and I talked about the interrupted method. And you can use this method to see if the current thread has been interrupted. And if it has, then it goes ahead and returns true, and it clears, in either case, it clears a flag that keeps track of the interrupt status. Okay, so that's basically what's going on in the background in one or more pool threads that are doing the computations on all the prime candidates. Now let's take a look at what else is going to happen here when we kick things off from the user interface thread. So what's going to happen here is we're going to create a list of futures that will ultimately be used to store the results of concurrently checking the primality of a bunch of random numbers within a certain range, where the range will have duplicates. So we're going to have a list of futures as a result of the operations we're about to initialize using a Java sequential stream. So we have a list of future to prime result. So here's what it looks like. We make a new random number, and we use that random number to generate a stream of longs of up to count. Count longs will be generated random, and they'll be in the range of S max value minus count to S max value. And S max value is a very large number, like 1 billion or something like that. And that way we will be assured if count is large, we'll end up generating duplicate values in that range. And you'll see why we want duplicate values later. We then take that range of large prime numbers, large random numbers, and we call map to ob. So map to ob is a Java stream intermediate operation that will take a stream of, in this case, longs, and then map them to objects. And what they're going to be mapped to will be new instances of the PrimeCallable class. Remember we saw PrimeCallable? And if we scoot back here just a second to PrimeCallable, you'll see that there's a constructor here that takes a prime candidate and stores it in a field. And so what happens here is that each value in the stream, each long value in the stream, will have a new PrimeCallable wrapped around it, and we'll end up with a stream, the output from this map to obj intermediate operation will be a stream of PrimeCallable objects, each of which is associated with some large random number. That stream of random numbers is then fed into the map operation. So the map operation is going to take a stream of objects, and it'll create a stream of objects, and there'll be the same number of objects coming out in the output stream as there were in the input stream, but they're going to be of different types. Just like these are of different types. This was a stream of longs that was converted into a stream of PrimeCallables. And now we convert the stream of PrimeCallables into a stream of futures to prime results. And the way that that happens is we end up calling the submit method reference, or passing the submit method reference into the map as the behavior we want executed. So for every PrimeCallable, we will submit each PrimeCallable one at a time to the executor service via its submit method. And submit, of course, if you recall, we'll go ahead and stick that request at the end of the queue, the work queue inside the executor service thread pool. And then some thread in the pool will wake up and pull it off when it's ready and run it. Now what comes back from submit is a future to a prime result. So we'll end up here with a stream of futures to prime results coming out of this map intermediate operation. And each future, of course, will represent the pending task results that will come back once the threads process the PrimeCallables in the thread pool. So the last thing that we do is we take this stream of futures to prime results, and we collect it, and we turn it into a list of futures to prime results. So we're going to go ahead and collect everything in the stream up into a data structure, which will be a list. So we'll end up with a list of futures to prime results as a consequence of doing this little sequential stream. So basically what we're doing here is we're generating random numbers, converting them to PrimeCallables, passing them off to the thread pool to be executed, getting back futures, and then storing those in a list. So we end up with a list of futures to prime results as a result of this. And I think that is just so cool, right? This is so clean and concise, and you really no extra stuff. You sort of just can read it once you know how to read streams, syntax, and know the semantics of streams. It's just really straightforward. No if-else statements, no loops, no need to initialize the list. It's all done by the magic of collect. So it's a very powerful example of using Java functional programming features to do the main program here. We now have to have a way to collect the results, because we're going to have this list of futures. So we're going to have this class called FutureRunnable, and it's going to run in the background thread, and it's going to be used to get all the results of the futures as they finish being processed in the background by the thread pool. It implements the runnable interface, which means we can execute it in a thread. We keep a list of futures here as a field, and that, of course, is going to get set here. We're going to keep a reference back to the activity that created us. The constructor basically takes in the activity and the list of futures and stashes them away in the two fields. And here is the run hook method. This is the thing that will get the results. So this runs in the background thread and will get the results of the futures as they complete. Run is the hook method that runs in the background thread. As you can see, what it's going to do is it's going to iterate through all the futures one at a time. So for each future in the list of futures, we're going to go ahead and do the following. And this is a little bit funky looking at first, but it's really, really cool. So what we're going to do here is we're going to go ahead and call the get method. And future : get is the get method on the future interface. And the semantics of the get method are it will block until the future it's waiting on has been completed. And the future will be completed, of course, when one of the threads in the background in the thread pool finishes checking to see whether that number is prime or not. So when that computation is done, then the get method can return because the future's been triggered or completed. Now, we also do some really clever things here using a type exception laundering adapter, which converts future get, which expects a checked exception, into something that takes a runtime exception, which is really super cool. So this converts this into a supplier, and then we go ahead and get the results of that. So when this call returns, we will get the prime result. And then all we have to do is check to see whether or not that prime result was 0 or non-zero. If it's 0, it means it was a prime number. If it's non-zero, it means it was the smallest factor. So there's some code in there I'm going to omit unless you want to go look at it yourself. that prints the results out. And of course, it uses the activity in order to know where to print the results. When we're all done, we tell the activity we're out of here, and then the program can return and shut down or wait for the next request. Here's the fun part that causes interrupts to occur. So if the user was to click the little interrupt icon on the user interface, the floating action button with a little X on it, then that is associated with this method, interruptComputations. And as you can see what this method does when it's called, when the user presses that cancel button, it shuts down the executor service now, which means that it shuts it down abruptly, says, terminate yourself immediately, do not pass go, do not collect $200, just wrap up. And then it goes ahead and interrupts the background thread, the one that is waiting to get the futures. And remember, when shutdown now is called, that will set the interrupted status flag and all the threads in the thread pool, and then the isPrime method will detect that using the technique we talked about when we talked about isPrime. This thread shuts down, so the background thread is interrupted, and then we wait for up to half a second for everything to shut down. Because even though we told it to shut down now, it still might take a little bit of time to shut down. So we wait for up to a certain amount of time until everything's finished, and then we can go ahead and exit this particular run of the program gracefully. The next discussion is more of an Android-centric thing. So in Android, if you rotate the phone, the current activity is destroyed, and then a new one is created with either portrait or landscape mode, depending on which way you rotated to and which way you rotated from. We want our threads to keep running in the background even while the destruction of the current activity takes place. And so to do that, all the thread-centric state is bundled up into a class called RetainedState. And it includes things like the Executor Service instance, the FutureRunnable, and the thread. And all those things are kept in memory, and then we use this very clever technique to initialize the fields of the RetainedState object, which is an instance of RetainedState class. And we store all the various thread-centric fields in that object. So we store the FutureRunnable, we store the thread, we store the Executor Service, and so on. And all that stuff is running in the background, but it's all stored in one object. And then there's some cool hook methods which have ridiculously long names, like onRetain non-configuration instance, which is quite a mouthful. And this is used to load and store RetainedState when Android activities are created and destroyed as a consequence of runtime rotation changes or configuration changes. I won't belabor this, it's more of an Android thing, but it's a really cool technique, and you can use it to keep your program doing stuff in the background while you're changing the orientation. So like if you're playing a YouTube video, for example, and you rotate the phone, you don't want the video to stop and start over again at the beginning. You want it to keep playing and just have the orientation changed. Okay, so that's the end of the PrimeChecker app discussion for Executor Service.